So what's going on with this wave? What makes the string go up and down? And you know there's going to be some forces here, and we're going to look for the sum of the forces equals mass times acceleration. Here, there's no action. There's no motion. Why? Because if we look at a chunk of string, delta x with some mass, delta m, there's no force on it because we have a tension in this direction and an equal tension in this direction. Now that's different right here. Let's take this delta x. And we see here the tension is in this direction, but here the tension is pointing up. So there's a net force upward on this chunk of mass. So at this point, this mass feels a force upward. And it's going to accelerate upward. As this thing moves, this one will find itself up at the top at some point. Well, what's going on at the top? We have two tensions that have a vertical component downward. There's going to be a net force pulling downward on the top. So when the wave is right here, so this chunk of wave will accelerate upward and get to a point where it's this high. If we look at this chunk of wave, there's an equal and opposite tension. It's in equilibrium. Its velocity is constant, moving upward. You get to the top of the wave and you see you have two pieces of string pulling downward on it that have vertical components downward. It has a net force downward. It's going to accelerate downward. It comes to a rest up here, and then it begins to accelerate downward. When the wave has passed further, at this point, we see there is no force on the string because the tension is equal and opposite. And so this string will be moving downward with constant velocity. And why doesn't it overshoot? It doesn't overshoot because as the wave passes right here, we have a force pulling upward and a force here with no vertical component. So that force will accelerate it upward again and it will come to rest. So as the wave passes, a chunk of string will first feel this vertical component will accelerate upward. When it gets to the top, there's two components pulling it downward. It will accelerate downward. And then to bring it to rest, there's a component pulling it upward and it comes to rest, and this chunk of string is at rest in equilibrium. In order to solve this, we're going to have to use a small angle approximation, and that is that this theta is close to 0. What does this allow us to do? It will tell us that this length is the same as this length, that the cosine of theta is 1. It also allows us to say that because it doesn't get longer in any area, the tension is constant all the way along. Lastly, if this angle is very small, the horizontal component of the tension is the same everywhere. And so there's no horizontal acceleration and there's no movement. And if you watch a wave, what you'll see is as a wave passes, the particle only goes up and down. If you're laying in the ocean, when the wave passes, largely you just go up and down again. Okay, so what that tells us we can do is we can just say the vector sum of the forces in the y direction equals mass times acceleration in the y direction does not equal 0 because we accelerate up and then as a wave passes we accelerate down and we come to rest by accelerating up a little bit again. So how can we find the force acting on this chunk of string? Well, what we do is we look and we say, oh, we need to find the vertical components of the tension. We know the net force on this string comes from the tension pulling down here and the tension pulling up. But this one has a greater slope here, so this vertical component is going to be bigger. And so we take a look and we say yes. Here's the downward tension here. It's smaller than the upward tension here. And how do we find that? The y component of the tension is just equal to the tension times the slope of the line, dy dx. And so the sum of the forces acting on this chunk of string is just this vertical component minus that vertical component, or tension times dy dx at x equals x1, plus the force on the other side, which is tension times dy dx at x equals x2. Now this is in the opposite direction, so this would wind up being a minus, because this tension is pulling this way and this tension is pulling this way. So that's the sum of the forces. That must equal mass times acceleration. Well, what's the mass? When we talk about a string, it's not like a hanging mass, because we have a long distribution. And so we talk about a mass density that we'll call mu, and that's going to be in kilograms per meter. So it's the linear mass density. It's like if you go to buy a chain and someone says, how heavy of a chain do you want? You say, I want something that's going to be 5 kilograms per meter. This is equal to the mass per unit length. If you want to know the mass of this chunk of string, the mass is just going to equal the mass density times the amount of length that you have. And in this situation, because we're using the small angle approximation, this is about equal to mu times delta x. So now we can substitute in and say this is equal to mu delta x times the acceleration in the y direction. And I like that because we can pull this out now. And this is dy dx at one point, and this is dy dx at the other point. And we can divide through by delta x is equal to mu times the acceleration in the y direction. And I like this because this is the slope of the line at two different points. And so this is the change in slope, and this is the change in x. So this is the second derivative of y. Or we can write this now as t times the second derivative of y with respect to x is equal to mu times the second derivative of y with respect to t. This is a second time derivative. This is a second spatial derivative. And so I'm going to pull this over, and I'm going to write this as t over mu times d squared y dx squared is equal to d squared y dt squared. Now I have my equation of motion from dynamics, and now we're going to use that guess and check method. Let's put this function in here and see what we get. When we take the second derivative of this with respect to x and t, using the chain rule, these functions are going to give us the same result, except for this is going to take a derivative with respect to x, and this is going to take a derivative with respect to t. And so both of these are going to be the same, except this is going to have a k squared come out, and this one is going to have an omega squared come out. And whatever else there is, the derivative of this is going to cancel. And so what I'll have then is, I'll still have the t over mu, and so now I have t over mu is equal to omega squared over k squared. But I remember from before, this is a wave number, meters per second, this is equal to the square of the velocity of the wave. And so the velocity of the wave is equal to the square root of tension over mu. And that might make sense if you think about it. It's the tension that gives us a force to accelerate the piece of string or the spring. And the acceleration will decrease if the mass is larger. Let's check units. Tension is in newtons, or kilogram meters per second squared, and mu is mass density, which is kilograms per meter. And so what do you have? You have kilograms cancel, and meters in the denominator, which come up into the numerator, and I have meters squared per second squared. I like it because this is square root, and that gives me meters per second. So using dynamics, we came up with this equation of motion, and we showed that any function of this form will satisfy that equation. And what I want you to do for homework is try this. Y is equal to some amplitude times cosine of kx minus omega t, and put it in there and show that this satisfies that equation.